The global energy industry is worth trillions of dollars, built on pipelines, tankers, refineries, and assumptions so old, most people never question them. Oil powers transport. Gas powers factories. Coal still props up grids. And even in a world obsessed with solar panels and electric cars, the hidden truth is that the modern economy still depends on fuel systems designed decades ago. That is why what happened in a remote stretch of China's Gobi Desert is making scientists, investors, and rival governments pay very close attention. Because this was not another battery demo. It was not another flashy prototype. It was a fuel breakthrough. And if it scales, it could change who controls the next era of energy. Here is the part most people have not heard. China did not just test a reactor. China says it has successfully converted thorium into uranium-233 inside an operating molten salt reactor, creating real-world proof for a fuel cycle many countries talked about for decades but never truly brought to life. That sounds technical, but let me translate it into plain language. Imagine finding a way to turn a more abundant material into usable nuclear fuel inside the machine that is already running, not in theory, not in a lab slide deck, in an operating system producing heat through fission. That is why this story has people in the energy world leaning forward. For years, thorium was treated like the almost mythic underdog of nuclear energy. People kept saying it was safer, cleaner, more abundant, more elegant, and then the conversation would stop, because saying something could work is not the same as making it work. Thorium is not directly fissile. You cannot just dig it up, drop it into a standard reactor, and expect magic. It has to be converted through a chain of reactions into uranium-233, which can then be used as fuel. That complexity is exactly why thorium stayed stuck in the realm of interesting, while uranium built the real nuclear industry. But China kept pushing, quietly, patiently, and now the details are hard to ignore. The reactor at the center of this story is called TMSR LF1, a 2-megawatt thermal thorium molten salt reactor in Wuwei, Gansu Province. Construction began in 2018. It was granted an operating license in 2023. It reached first criticality in October 2023. By June 2024, Chinese reports say it had reached full power. Then came the first major shock. In October 2024, scientists added thorium to a working molten salt reactor, something not previously demonstrated in an operating system. Then in late 2025, China announced the first successful conversion of thorium and uranium fuel in that reactor. That sequence matters, because it suggests this is not a one-off publicity stunt. It is a step-by-step campaign. And here is why the industry is uneasy. Once you show that fuel conversion can happen in an operating reactor, the conversation stops being, is this physically possible? And starts becoming, how fast can this be scaled? That is a completely different question. One question belongs to scientists. The other belongs to ministries, utilities, shipbuilders, chemical giants, and defense planners. This is the detail that changes everything. Because the real disruption is not just about electricity. Molten salt reactors are attractive because they operate at high temperatures and low pressure. That combination opens doors. You are not only talking about powering the grid, you are talking about industrial heat. You are talking about hydrogen production. You are talking about chemical processes that today still rely heavily on fossil fuels. In other words, this is not just an attack on one piece of the energy system. It is a potential challenge to several of them at once. And if you are watching from the United States, Britain, or Europe, the emotional sting is not hard to understand. Much of the early molten salt research was pioneered in the United States decades ago. Oak Ridge proved pieces of the concept in the 1960s. But then the West moved on, choosing other nuclear pathways and letting this branch sit on the shelf. China looked at that abandoned map and decided to keep going. That is part of why the story lands so hard. It feeds directly into a narrative a lot of viewers already feel in their gut. The uncomfortable idea that technologies once explored in the West are now being industrialized faster somewhere else. Here is what they are not telling you in the loudest headlines. This is not about China replacing every oil well tomorrow. It is not about gas stations disappearing next year. The real shock is subtler and more powerful than that. If thorium molten salt systems become commercially viable, they could reshape where future energy security comes from. They could reduce pressure on imported uranium. They could provide high-temperature clean heat for hydrogen and heavy industry. They could be deployed in places where conventional large nuclear plants are too expensive or too slow. And perhaps most importantly, they could give China leverage in a future energy stack that is not dominated only by oil and gas. That last point matters, because China's energy vulnerability has never been a secret. Even with all its domestic coal, renewable build-out, and industrial capacity, China still depends heavily on imported oil. In 2024, imported crude accounted for roughly 74% of the country's apparent oil consumption. That means energy security is not an abstract talking point in Beijing. It is a strategic obsession. When a country of that size looks at a fuel source that is more abundant than uranium and can potentially support carbon-free heat, electricity, and hydrogen, it is not viewing it as a science fair project. It is viewing it as insurance, leverage, and long-term resilience against outside pressure. So why are smart people still taking this seriously? Because China's progress appears to target the hardest part first, proving the fuel cycle in an operating reactor rather than endlessly describing the dream on paper. That matters more than flashy claims, and the reactor design itself has features that keep drawing attention. In a molten salt system, the fuel is dissolved in salt that also helps carry heat. Unlike traditional reactors that must periodically shut down and replace solid fuel rods, a liquid-fueled system can potentially be refueled online. Chinese reports say that in 2024, their team reloaded fuel without shutting the reactor down. If that can be done reliably and safely at scale, it changes the economics and operational logic in ways the old nuclear model never quite managed. But here is the part nobody should ignore, and it changes the tone of the whole story. Breakthrough does not mean victory. China may be ahead in demonstrating a thorium molten salt pathway, but the graveyard of energy history is full of inventions that worked just enough to make headlines and then failed in the cruel world of cost, corrosion, maintenance, regulation, and public trust. So the real question is no longer whether China created a dramatic moment. The real question is whether this moment can survive contact with reality. Because the second half of this story is where the fight begins. The reason the energy industry reacts so strongly to stories like this is simple. Everyone in the sector has seen revolutionary fuel claims before. Cold fusion, miracle hydrogen timelines, carbon capture overpromises, biofuel hype cycles, synthetic fuel dreams that collapse under cost. So when China announces a nuclear fuel milestone, skeptics immediately ask the same brutal questions. Can it scale? Can it compete? Can it survive the physics, the chemistry, the regulators, and the market at the same time? Start with the chemistry. Molten salt reactors sound futuristic because the fuel is liquid and the system runs at high temperatures without the extreme pressures associated with conventional water-cooled reactors. That sounds cleaner, smoother, smarter. But molten salts are chemically aggressive. They corrode materials. They challenge valves, pipes, seals, and containment systems. You are not just building a reactor. You are building a machine that has to survive years of radiation, high temperature, and reactive chemicals without slowly eating itself alive. That is not a minor issue. That is one of the core reasons molten salt designs were not commercialized decades ago. Chinese teams know this. Their 2-megawatt reactor is not just a power experiment. It is also a materials testbed. They are effectively asking whether they can build alloys and components that do not fail under these conditions. Because if the materials fail, the breakthrough does not matter. That is the hidden reality of advanced energy. The future is often decided less by grand ideas than by boring parts that refuse to survive long enough. Then comes the fuel cycle challenge. Thorium itself is fertile, not fissile. That means it needs a starter fuel such as uranium to get the reaction going until enough uranium-233 is bred from the thorium. That introduces complexity in design, handling, accounting, and long-term economics. It also complicates the clean, simple story often told online. This is not dig up thorium and get infinite energy. This is a carefully managed conversion process involving chemistry, separation, fuel management, and reactor control. It may still be transformative, but it is not magic. And then there is the issue almost every hype video skips: reprocessing and waste handling. Thorium systems are often praised for potentially producing less long-lived waste than conventional uranium systems. That is one reason the concept remains attractive. But less is not zero. Different waste streams still have to be managed. Radioactive materials still have to be contained. Fuel salts still have to be processed. Off-gases still have to be handled. And if you want a continuous or semi-continuous fuel cycle, you are adding another layer of operational complexity that utilities and regulators must trust. Here is what makes China's move so unsettling anyway. While the rest of the world is still debating theory, China is building learning curves. That may sound like a small distinction, but it is not. The country that gets the most operating hours, the most maintenance lessons, the most corrosion data, and the most real-world failures often becomes the country that knows how to commercialize. In advanced manufacturing, experience compounds. While critics are still laughing at the first prototype, the team on the ground is already solving the second and third problem, and that gap can become enormous before outsiders notice. This is why the roadmap matters. China is not presenting the 2-megawatt reactor as the endpoint. Multiple reports describe plans for a larger demonstration reactor in Gansu that would produce around 10 megawatts of electricity and roughly 60 megawatts of thermal output, with operation targeted around 2030. Longer term, Chinese planners have also discussed a 100-megawatt thermal demonstration project by 2035. If even part of that timeline holds, the story changes from interesting pilot to emerging platform. And once something becomes a platform, industries start reorganizing around it. Think about what that means. A reactor that can provide high-temperature heat is not just another power plant. It can feed chemical production. It can support low-carbon hydrogen. It can potentially serve industrial parks, remote regions, or even maritime applications. Chinese discussions have already mentioned hydrogen generation and even long-duration ship propulsion concepts. Now pause there for a second, because that is the kind of line many viewers hear and dismiss as science fiction. But that is also exactly how strategic technology shifts begin. First as a strange sentence, then as an experiment, then as an industrial reality most people did not see coming. Here is the fear that established energy players rarely say out loud. The danger is not that thorium suddenly wipes out oil demand next year. The danger is that it starts solving the hard sectors piece by piece. Industrial heat, chemical feedstocks, hydrogen production, remote stable generation, high utilization clean power. If a technology begins entering those spaces, it does not need to replace everything to become dangerous. It only needs to carve out enough of the future to redirect capital, policy, and talent. And capital follows momentum. Once governments believe a technology could matter strategically, they do not wait for perfect certainty. They fund ecosystems. They train engineers. They rewrite regulations. They create national champions. They secure materials. They shape supply chains before the rest of the world finishes arguing about feasibility. China has done this in solar, batteries, EVs, and parts of the grid equipment industry. That pattern is why people are paying attention now. Not because the outcome is guaranteed, but because the playbook is familiar. But there is another side to the story, and most people never hear this part. Thorium's strongest selling points can also become political vulnerabilities. One of them is proliferation risk. Supporters often argue thorium cycles are less attractive for weapons than traditional pathways. Critics counter that uranium-233 can still present serious proliferation concerns and must be safeguarded carefully. That means any large-scale thorium economy would still need tight monitoring, international trust, and robust security architecture. In other words, even if the physics work, the politics remain difficult. And if you are a viewer who thought this was just another crazy future reactor video, here is the punch that should hold your attention. China's oil dependence is still enormous. Its manufacturing base still needs reliable energy. Its leadership talks constantly about keeping critical energy supply in its own hands. So this is not just a prestige science project. It fits a deeper strategic logic. A country that wants resilience does not want only more solar panels. It wants controllable, domestic, scalable energy options that reduce external pressure over time. That is why this breakthrough, even if imperfect, is already changing behavior. It is pulling attention. It is forcing comparisons. It is reviving questions that much of the West had quietly put aside. And once a question like this comes back, it rarely disappears. The world is now being asked something it did not expect to confront so soon. What if the next important fuel race is not oil versus renewables, but old nuclear versus a new generation of fuel cycles that only one country has seriously operationalized? And that leads to the most important question of all. If China is first to build the expertise, the supply chain, and the industrial confidence around thorium molten salt systems, what exactly happens to everyone else? This is where the story stops being about a reactor and starts becoming about power. Because history shows that whoever masters a new energy system does not simply gain cheaper electricity. They gain manufacturing leverage. They gain diplomatic leverage. They gain narrative leverage. They get to say the future runs through infrastructure they understand better than anyone else. That is the deeper reason this breakthrough feels shocking. It arrives in a decade where the West has already been forced to watch China dominate solar manufacturing, expand battery control, push aggressively in electric vehicles, scale grid hardware, and move fast in industrial policy. Now add a possible advanced fuel cycle to that list. Being early matters. Early movers write standards. Early movers attract talent. Early movers shape which risks are solved first. And snowballing is exactly how industrial gaps become geopolitical gaps. First, a country looks slightly ahead. Then it becomes the place with the most operating experience. Then other countries depend on its components, its contractors, its expertise, or its financing. By the time rivals decide the technology is real, the ecosystem already exists somewhere else. That pattern is not theoretical anymore. We have watched versions of it happen before. So imagine the next decade, if China's thorium program keeps advancing. The 2-megawatt reactor keeps delivering data. The larger demonstration unit comes online near 2030. Materials improve. Online refueling becomes more routine. Regulators gain confidence. Industrial partners begin building around the heat output. Hydrogen projects attach themselves to the platform. Maritime or remote energy demonstrations start to appear. None of that requires a miracle. It just requires consistent iteration. And iteration is how technological leadership is usually built. Now imagine the opposite side. Western countries continue to discuss, publish, debate, and wait. Private companies announce concepts but struggle to get permits, financing, or supply chains. Political cycles disrupt continuity. Nuclear debates stay trapped between nostalgia, fear, and bureaucracy. In that world, China does not need to be perfect. It only needs to be faster. Here is what most people miss when they hear breakthrough. They imagine a dramatic moment where one invention instantly replaces another. Real disruption is colder than that. It begins by changing expectations. Investors ask different questions. Governments fund different programs. Universities train different specialists. Military planners assess different scenarios. Industries that looked secure suddenly feel less permanent. That is how a future arrives before the headlines admit it. And the existing energy giants understand this better than anyone. Oil and gas companies know that long-term threats do not always come from immediate substitution. Sometimes they come from technologies that attack demand on the margins first, then spread. If advanced reactors make hydrogen cheaper in certain settings, that matters. If they provide industrial heat without combustion, that matters. If they reduce the strategic fear of imported fuel dependence, that matters. The threat is cumulative. This is also why the emotional hook of this story is so strong. It plays directly into two anxieties at once. The first is disbelief. Most people had no idea China was this far along with thorium molten salt systems. The second is recognition. Once they hear the details, it fits a larger pattern they have already been watching. China sees an abandoned or underestimated technology, builds patiently, scales relentlessly, and suddenly forces the rest of the world to react. Whether you admire that or fear it, the narrative is powerful, because it feels familiar. But let's stay honest, because that honesty makes the story stronger, not weaker. This breakthrough does not erase the obstacles. Thorium still faces serious questions of cost, chemistry, fuel handling, and proliferation safeguards. Large-scale deployment is not guaranteed. Public acceptance of advanced nuclear varies widely. Grid economics are changing fast. Competing energy technologies are improving every year. And governments have a long history of overpromising on energy miracles. All of that is true. Yet none of those caveats erase the significance of what China appears to have done. It has moved thorium out of the purely speculative category and into credible enough to matter. That phrase may not sound dramatic, but in energy strategy it is explosive. Once something becomes credible enough to matter, no rival can safely ignore it. They can dismiss the timeline. They can question the economics. They can argue about the risks. What they cannot do anymore is pretend the race does not exist. And the race may widen from here. If China can show that thorium molten salt systems work not only for heat, but for hydrogen, maritime use, or modular deployment in energy-hungry industrial zones, then the discussion expands far beyond nuclear specialists. Suddenly, steel, chemicals, transport, shipping, and national security all want a seat at the table. Suddenly, this is not a reactor story. It is a systems story. That is why the closing question matters so much. Not, will thorium replace oil by next year? That question is too shallow. The real question is this: has China just opened a new strategic lane in energy that the rest of the world underestimated for too long? Because if the answer is yes, then the consequences arrive long before mass deployment. Money moves. Research priorities shift. Alliances adapt. And countries that assumed they had time realize the gap is already forming. While people are still arguing online about whether this is overhyped, China is collecting data, improving materials, and planning larger systems. That is the part that should make viewers sit up. In technology races, delay often feels harmless, right until it becomes irreversible. The distance between interesting prototype and industrial lead can shrink very fast when one side is learning in the real world and the other side is mostly talking. So what happens next? Maybe thorium remains a niche platform. Maybe costs stay too high. Maybe corrosion and fuel cycle complexity slow everything down. Maybe other advanced reactors leap ahead. Those are all possible outcomes. But here is the one outcome that is no longer believable: that this can be ignored. China has already changed the conversation. It has demonstrated that a fuel long treated as a futuristic side note may have a real pathway into the strategic energy landscape. It has reminded the world that the next energy shock may not come from a bigger oil field or a better battery ad. It may come from a country that quietly took an old idea, solved enough of the hard parts, and forced everyone else to look up. And that may be the most unsettling detail of all. The energy industry was expecting a transition. It may not have been expecting this transition to include a new fuel cycle, a revived reactor concept, and a country determined to turn both into leverage. So the next time someone tells you the future of energy is already decided, remember what happened in the Gobi Desert. Because sometimes the biggest disruption does not arrive with a global announcement. Sometimes it starts in a place most people are not watching, inside a machine most people do not understand. until one day the entire industry realizes the question has changed. And once the question changes, the balance of power can shift very quickly with it.